Dear students, we are in the fifth part of stereochemistry. In first four parts, we have seen about the definitions of stereochemistry, its classifications into structural isomerism as well as stereoisomerism. We have seen different types of structural isomers and different types of stereoisomers. Then we had seen about molecular projections, and today we had also seen about the different types of interconvergence of molecular projections. Now today we will see about the optical isomerism. So first let us see just recapitulation of what is stereoisomerism. The isomerism arising due to difference in spatial arrangements, difference in three-dimensional arrangement of molecules or atoms or groups of atoms in the molecule is called as stereoisomerism. The stereoisomerism is of two types, a configurational isomerism or a conformational isomerism. Configurational isomers are those which can be interconverted by breaking the bond and then attaching the bond in a different angle. So that will be configurational isomers. Conformational isomers are those which can be interconverted just by rotation or through carbon-carbon single bonds. Configurational isomers are of two types. One is geometrical isomers and other is optical isomers. Today we will be seeing about the optical isomerism. Optical isomers rotate the plane of plane polarized light by a certain angle. So this may have same or different physical and chemical properties, but they will rotate the plane of plane polarized light in different angles. So they will be rotating the plane of plane polarized light by a certain angle. This phenomenon is called as optical isomerism, and the compounds exhibiting this optical isomerism are called as optically active compounds. The isomerism arising this is due to the difference in spatial arrangement of atoms or group of atoms on a tetrahedral carbon. For example, we can have the example of a lactic acid, which the central carbon atom, tetrahedral carbon atom, has one hydrogen, hydroxyl group, carboxylate group, as well as the methyl groups are the four substituents. Now, these four substituents can be arranged either in this way or in its mirror image way. When we put a mirror over here, the other one will be looking as similar as a mirror image of the first one. So in this case, both of them are different, as this is Fisher projections. So this OH and H are towards our side, while COH and methyl groups are away from us. So when we put it, these two are somewhat like this. So these are the mirror images. We cannot put it one over the other like this. But what we can do is that we can just put it over here in this way. But this way also our white side will be coming over the means it will be superimposed over the black side, and the back side will be coming towards the front side. So exactly we cannot superimpose these two mirror images together. Such mirror images are called as non-superposable mirror images. We will see this non-superposable mirror images a little while later in different other lectures. But just remember this word non-superposable mirror images. These are optically active compounds. Those which are non-superposable mirror images are always optically active compounds. So optical activity was first discovered by Bayet in the year 1815. So it is more than 200 years technology, 200 years discovery. And when Bayet was studying crystals of quartz, he encountered two types of crystals of quartz. One rotating the plane of polarized light in a anti-clockwise direction, and the other rotating it in a clockwise direction. So the quartz crystals were rotating the plane of plane polarized light either in a clockwise direction or in an anti-clockwise directions. So this he observed later that this is not the property only of solids or crystals, but it is also a property of solutions also. So solutions also exhibits this property, and hence this discovery came of optical isomerism. But it was major work of Louis Pasteur which made it more uh, active, more useful for organic chemistry, when he was studying different crystals of sodium ammonium tartarate. When he was studying the crystals of sodium ammonium tartarate, this sodium ammonium tartarate can exist in two different ways, one in a trio isomer, the other in a erythroisomer. Just in the last lecture we had seen about what is threo and erythro of tartaric acid, and you were also asked about how means interconvert this into Fischer to Newman, Newman to Sohor's projections of tartaric acids, both the threo as well as erythro isomers. These threo and erythro isomers crystallizes in different forms. They are mirror images of each other, so their crystals are also mirror images of each other. Louis Pasteur separated these mirror images of each other, these two types of crystals, manually, and then he studied it along the plane polarized light. The solutions he prepared after separating the two crystals manually, he dissolved them into different solutions, prepared different solutions, and then he studied it with the plane polarized light. And what he found that each of these is the mirror images rotates the plane polarized light in a opposite directions. That is, if this is rotating it in a clockwise direction, the other will be rotating in a anti-clockwise direction. So if one is rotating in a clockwise direction, the other will be rotating in a anti-clockwise direction. The plane polarized light is being rotated either in the clockwise direction or an anti-clockwise direction. The optical isomers may or may not have similar physical and chemical properties, but they differ in their interaction with plane polarized light. They may have similar physical properties or similar chemical properties, or may not have similar physical and chemical properties, but their interactions with plane polarized light are definitely different, and that is why they are called as optical isomers. Many of them show different chemical properties when they are reacted with other optically active substances, but with non-optically active substances or optically inactive substances, they show same chemical behavior. That is, their chemical properties are same if they are reacting with a chemically inactive substances, but when they react with chemically active substances, their properties differ. So this is an important discovery, the optical isomerism and that's phenomenon. So Louis Pasteur is credited for this work. So first we will see what is polarized light, and for that first we have to see what is light. Light theories were given by first Newton, and then it was in the 18th century. In 19th century we were given by Maxwell the theory called as electromagnetic radiations. This we have studied it in physics, electromagnetic wave theory or electromagnetic radiations. According to this theory, light consists of both electric field as well as magnetic field. Let's say this E is electric field and B is represented by a magnetic field. Here the blue lines are the electric field and the red lines are the magnetic fields. Both the blue lines as well as red lines, that is electric field and magnetic fields, are perpendicular to each other. That is, we can show it in this way. They are perpendicular to each other. If this is our electric field, this will be our magnetic field, and the propagation of this light will be perpendicular to both of them, that is along the other direction. That we can say it as a wavelength will be on the other direction. It will be somewhat like this, where one direction, that is propagation of wave, will be in this direction, then the magnetic field will be projected over here and the electric field will be projected up, so that all the three are in the perpendicular direction to each other. But this is not the only thing that happens. But when it is an unpolarized light is there, that is an ordinary light, when it comes out, its electrical field is not directed only in one direction, but it is sometimes the other rays will be having each ray will be having a different direction of the electrical field. So when we take a full light, complete bunch of light, then that beam, incident beam, will be unpolarized light, where the electrical field components will be projected in different directions. So this different directions we can individually make it like this. So this we call it as a unpolarized light, where the electrical field is projected in different directions. In any possible direction, the electrical field will be projected. Similarly, the magnetic field will be always perpendicular to the electrical field, and so the magnetic field will also be projected in the all possible directions. For an individual ray of light, जिसका मैग्नेटिक फील्ड अगर इस तरफ होगा तो उसका इलेक्ट्रिकल फील्ड उसके परपेंडिकुलर में होगा। लेकिन जब हमारे पास n नंबर ऑफ रेज होते हैं तो किसी एक का मैग्नेट इलेक्ट्रिकल फील्ड इस तरह से होगा तो दूसरे का इलेक्ट्रिकल फील्ड इस तरह से होगा, तीसरा ऐसा होगा, चौथा ऐसे होगा। सो वी हैव ऑल n number of directions will be there for electrical field. So this is called as a unpolarized light or a non-polarized light, where the electrical field का जो directions है वो सारे अलग अलग directions में होता है। So ये unpolarized light होता है, इसको हमें polarize करना होता है। पोलराइज करना है मीन्स इसका जो इलेक्ट्रिकल फील्ड है वो किसी एक ही डायरेक्शन में प्रोपगेट करना है हमें, ना कि ऑल पॉसिबल डायरेक्शन। So we have to show or we have to make it in such a way that only the rays which are having electrical field in one direction will be passed through it, the others will get reflected back or will get absorbed itself. So that can be done by using a Nicol's prism. Nicol's prism is the one which you have studied it in your physics classes also, that when a ray of light is passed over here, it either passes, emits outside, or it may get total internal reflection. So depending on द इलेक्ट्रिकल फील्ड का जो ओरिएंटेशन होगा, उस ओरिएंटेशन को देखते हुए किसी एक ओरिएंटेशन को ही वो बाहर आउट करेगा, बाकी सबको वो अंदर टोटल इंटरनल रिफ्लेक्शन में होगा। सो अगर आपका ये लाइट जो इंसिडेंट लाइट है उसका इलेक्ट्रिकल फील्ड इज अनपोलराइज्ड और नॉन पोलराइज्ड इलेक्ट्रिकल फील्ड है, तो जो आउट होगा, बाहर जो आएगा, उसका इलेक्ट्रिकल फील्ड किसी एक ही डायरेक्शन में होगा, नॉट इन ऑल पॉसिबल डायरेक्शन। So what we call is that this is our unpolarized light and this is now polarized light. So after coming out of the Nicol's prism, the unpolarized light has become polarized light, जिसमें उसका इलेक्ट्रिकल फील्ड एक ही डायरेक्शन में है और उसका मैग्नेटिक फील्ड भी उसके परपेंडिकुलर में है, इसलिए वो भी एक ही डायरेक्शन में है। सो इलेक्ट्रिकल फील्ड एंड मैग्नेटिक फील्ड दोनों एक ही डायरेक्शंस में है, मींस perpendicular to each other, but they are in one single directions oriented. So this is how the plane polarized light can be obtained when a source containing non-polarized light or unpolarized light, when it comes and passes through a polarizer. This polarizer can be Nicol's prism or a quartz prism, we can have it. So when it passes through Nicol's prism, it allows only the rays of light which are having its electrical field oriented in a one particular direction. So we will have this plane polarized light will be coming out of the polarizer. So this is how we can obtain a plane polarized light. Now when this plane polarized light is passed through a sample, this is our setup for a polarimeter. Polarimeter is used for measuring the angle of rotation caused by the optically active materials. So here what we are doing is we are having an ordinary source of light. Here we are having a source of light which emits an ordinary unpolarized light or an ordinary light. So it is giving us an unpolarized light. This unpolarized light then passes through polarizer, which is generally a Nicol's prism. It passes through a polarizer and it becomes a plane polarized light. So it becomes a plane polarized light after it passes through a polarizer or a Nicol's prism. Now this plane polarized light is allowed to pass through a sample, and this sample is a solution which is containing optically active substance, so that the light, when encounters that optically active substance, it will be rotating this plane of plane polarized light either in the clockwise direction or in the anti-clockwise directions. So depending on your substance properties, this plane polarized light will be rotated either in a clockwise direction or in an anti-clockwise direction. So then whatever the light will be coming out, that light will be having its plane of polarization tilted either in a clockwise direction or in an anti-clockwise direction, so that we can further detect using a detector that what is the angle of rotation when we are not having any sample here and when we are having a sample. So सैंपल रखने से पहले हम इसको एक बार मेजर करेंगे कि कौन से एंगल में ये लाइट आ रहा है, और जब सैंपल रखते हैं उसके बाद में हम मेजर करेंगे कि उसका एंगल क्या हुआ, मींस कितने एंगल से वो रोटेट हो गया. So that way we can find out the angle of rotation, and this total whole setup is called as a polarimeter. This polarimeter is used to measure angle of rotation of an optically active substances. This plane polarized light or this unpolarized light, when it passes through a polarizer, becomes a plane polarized light when it passes through substance, and then through analyzer we can find out whether it has rotated in an anti-clockwise direction or a clockwise direction. Here this has rotated in an anti-clockwise direction, this has rotated in a clockwise directions. So there are then two types of substances are there. One which rotates the plane polarized light in a anti-clockwise direction, and the other which rotates in a clockwise direction. So that those substances which rotates in a clockwise direction are called as dextro-rotatory, or they are nomenclated as small d or plus sign. They are nomenclated either as a small d or plus sign. The small d is very important. Do not use it capital D. Capital D we will be using it somewhere else. So this is either a small d or a plus sign, or it is simply called as dextro-rotatory if the plane of plane polarized light is rotated in a clockwise direction. If it is rotated in an anti-clockwise direction, it is called as a laevorotatory and is symboled as small l or with a minus sign. Minus sign or a small l denotes laevorotatory, that is anti-clockwise rotation of the plane polarized light. So this is how the polarimeter works. Then when there is angle of rotation is there, that is through either in a clockwise direction or in a anti-clockwise directions. In both ways, either in a clockwise direction dextro-rotatory or anti-clockwise directions levorotatory, there will be a certain angle of rotation or the optical rotation will be there. This optical rotation is a property of individual molecules. So as it is a property of an individual molecule, so the light which encounters more number of molecules will be rotated but through a more angle. If it is encountering less number of molecules, it will be rotated through a less angle. So the total rotation caused by a solution will depend on the number of molecules encountered by plane polarized light in its path. That is, it will depend on the concentration and the path length. If the path length is L and concentration is C, if C is expressed in terms of grams per ml per cm cube, and if L is expressed, that is length is expressed in terms of decimeter. Decimeter is equal to 10 centimeters. If it is expressed in terms of decimeter and C is concentration is expressed in terms of grams per ml, then theta, the angle of rotation, is proportional to C into L. Theta is proportional to C into L, or theta will be equal to some constant alpha into C into L. Some constant alpha into C into L. This alpha depends on the wavelength of light that we are using it and the temperature at which the experiment is being carried out. So we denote it by a square bracket alpha with a subscript lambda and superscript as a T. T denotes temperature and lambda as a wavelength of the light used. So we can have this as alpha lambda t will be equal to theta upon L into C. This formula, that is alpha lambda t equals theta upon L into C, gives us the specific rotation of a individual sample, gives us a specific rotation of an individual sample. Specific rotation is the angle of rotation when L is equal to 1 decimeter and C is equal to 1 gram per ml. When concentration of the solution is kept at 1 gram per ml and the path length of the tube is kept at 10 centimeter or 1 decimeter, then whatever the angle of rotation we get it, that angle of rotation we call it as a specific rotation. So this specific rotation is defined as the angle of rotation produced by a solution of concentration 1 gram per ml, which is placed in a polarimeter with a tube length of 1 decimeter. The specific rotation depends on the nature of substance, temperature and wavelength, and that is why we have it in the formula alpha lambda T. So T denotes the temperature, lambda is the wavelength of the light, and the sample nature of substance will denote how much is the rotation is there. Generally, we use sodium D line light, that is having two lines, one at 589 nanometer and other at 589.6 nanometer is used as a source of light. We generally use sodium lamp as the source of light for polarimeters. The specific rotation, the optically active substances, as we have seen it, can rotate the plane of polarized light in either clockwise direction or anti-clockwise direction. If it rotates in a clockwise direction, they are called as dextro-rotatory and they are denoted by small d or plus signs. If the optically active substance rotates the plane of plane polarized light in an anti-clockwise direction, then that is called as a levorotatory or small l or minus sign. So we can have either in a anti-clockwise direction as a levorotatory or a clockwise direction as a dextro-rotatory. So we can have two different substances. The substance being a dextro-rotatory or a levorotatory can only be found experimentally by using polarimeter. This is very important because we cannot assign the small d or small l or plus or minus sign just by observing the structure of a molecule. सिर्फ स्ट्रक्चर को देख करके हम ये नहीं बता सकते हैं कि ये मॉलिक्यूल डेक्स्ट्रो रोटेटरी होगा या लीवो रोटेटरी होगा. सो लीवो रोटेटरी या डेक्स्ट्रो रोटेटरी ये सिर्फ हमें एक्सपेरिमेंट करके ही पता चलता है, बाकी ऐसे ही सिर्फ स्ट्रक्चर देख के पता नहीं चलता है. सो दिस इज एक्सपेरिमेंटली डिटरमाइंड क्वांटिटी, नॉट अ थियोरेटिकली डिटरमाइंड क्वांटिटी. जस्ट स्ट्रक्चर देख करके किसी का भी हमें पता नहीं चलेगा कि वेदर इट इज ए डेक्स्ट्रो रोटेटरी और अ लीवो रोटेटरी. Let us solve some problems of specific rotation. How to determine specific rotation? So calculate a specific rotation of 20% sugar solution which rotates plane polarized light by an angle plus 39 degree when passed through a cell of width 10 centimeter using sodium D line as light source. Is the sugar solution dextro or levorotatory? This last one we will see it later. First we will find out what is the specific rotation. Specific rotation के लिए या कोई भी प्रॉब्लम के लिए सबसे पहली चीज होती है कि हमें यहाँ पे given quantities क्या है वो लिखना है. We have to first write it given quantities. So कोई भी अगर आप प्रॉब्लम सॉल्व करते हो तो पहले यहाँ पर given quantities लिखो. Given quantities में हमारे पास क्या है, एंगल ऑफ रोटेशन हमें दिया है, calculate specific rotation of a 20% solution of sugar solution which rotates plane polarized light by an angle of plus 39. So हमें theta दिया हुआ है plus 39 degrees. So that is our angle of rotation. Then we have a concentration हमें दिया गया है 20% sugar solution. So C हमको find out करना है, directly नहीं दिया है, but it is a 20% solution. So we have been given 20% solution. So what is C? C is 20% means it is 20 grams per 100 ml. 20 grams in 100 ml will be giving rise to 20%. 20 per cent. Cent means 100. So 20 per 100 ml. So this will be our 20 grams per 100 ml. That is, we can find out as 0.2 grams per ml. If we divide this by 100, that is 20 divided by 100 will be giving rise to 0.2. So 0.2 gram per ml will be the concentration. So C will be equal to 0.2 gram per ml. We have to have the concentration being expressed in terms of grams per ml. Concentration must be in grams per ml. L should be in decimeters. So here C is in grams per ml. Then we have L being given to us when passed through a cell of width 10 centimeter. So 10 centimeter, we want it in decimeters. 10 centimeter is equal to 1 decimeter. So this will be equal to 1 dm. So now we have all the quantities, required quantities. Our formula is alpha lambda t is equal to theta upon L into C. This carries 1 mark just writing formula. Then this will be equal to theta is 39 divided by, this is L is 1 into 0.2. Now when we do this, it will be 390 divided by 2. When we multiply and divide by 10, so this will become 390 and 0.2 will become 2. So this will be equal to 195, and the units will be, this is expressed 39, or theta is expressed in degrees. So degrees, L is expressed in decimeter and it is in denominator. So per decimeter, C is expressed in grams per liter per ml. So it will be per gram ml. ml is denominator, so वो numerator में चला जाएगा. So we have this as a total specific rotation. Specific rotation lambda t will be equal to 195 degrees per dm cube per decimeter per gram ml. So this will be our specific rotation. This is how we can calculate specific rotations for any given substance. If we have the concentration being given to you, just concentration कुछ भी हो, आपको उसे ग्राम्स पर ml में लेकर आना है. यहाँ पे क्या करना है, जितने भी ग्राम्स दिए गए हैं डिवाइडेड बाय जितने ml टोटल सोल्यूशन है उसको डिवाइड करो, तो आपको ग्राम्स पर ml में मिल जाएगा सोल्यूशन. सो कॉन्सेंट्रेशन आपको मिल जाएगा, और जो आपका लेंथ है वो पाथ लेंथ है, उसे आपको डेसीमीटर में कन्वर्ट करना है. 1 डेसीमीटर इज इक्वल टू 10 सेंटीमीटर, ये याद रखना है, और फिर वो वैल्यूज को सब्स्टिट्यूट करो, यू गेट द फाइनल आंसर. So this is one problem that we had seen it. Now second problem is for homework or for home assignment to you. 9 gram of histidine amino acid. Histidine is one of the essential amino acids present in our proteins. This 9 gram of histidine amino acid is dissolved in 250 cm cube of or 250 ml of water and is taken for measurement of optical rotation using polarimeter of 10 centimeter long sample tube. Calculate the specific rotation of the solution if optical rotation is plus 23.4. So here you have been provided volume is given, gram is given, so gram upon ml you will be doing it. 9 upon 250 will give you the concentration. 10 centimeter length है means 1 decimeter ये है, और ये आपको थीटा दिया गया है. So you can easily calculate the specific rotation for this. This will be your for assignment. You have to do it for the assignment. One part we just missed it over here, that is the sugar solution dextro or laevorotatory. Dextro और laevorotatory हम सिर्फ यहाँ पे ऑब्जर्व करके ही पता चल जाएगा हमें कि एंगल ऑफ रोटेशन अगर प्लस है then it is a dextrorotatory, if it is minus then it will be a laevorotatory. यहाँ पे हमारा plus 39 degrees है, so this is a dextrorotatory. Our molecule is a, our sugar solution is a dextrorotatory. Our molecule will be a dextrorotatory molecule. That is a sample is a dextrorotatory sample which rotates the plane of plane polarized light in a clockwise directions. So one problem we have solved it. The other similar problem you have been you have to submit it through assignments. So thank you very much.